Hello, ladies and gentlemen, statistical minds of all kinds, and welcome to Statistical Minds, tonight's highly anticipated debate between Bayesians and frequentists. I'm your moderator, Gebhardt. Tonight's Bayesian has helped out the world in many ways, from breaking the unbreakable code to pioneering AI in modern computers. I give you cause and event. And our frequentist tonight has predicted the validity of many claims made by advertisers, keeping consumers safe everywhere. Miss Significance. It's Sina, actually. It's Danish. Okay. Sina. Sorry. Shall we move to the first of the questions today? This is for cause and event first. Then, for significance. Tell the statistical minds of the world a little about your statistics. What's its history?
Well, Reverend Bayes created his legendary formula, but abandoned it for unknown reasons. It wasn't until 1774 that Pierre-Simon Laplace independently reached it and became widely used. Frequentists, like Miss Vacance, shot down the equation for being too guess and check. But when World War II came about, the formula was revived, but in secret. Most famously, Alan Turing, the man who created the Turing machines, which would later become computers, used Bayes' theorem to break the Enigma code. You see, he would enter information from intercepted German messages into the machine, and then would calculate the most probable outcome and run it. It was brilliant, yes, quite, and since...
Yes, thank you, Miss Event. Now on to you, Miss Vacance. Well, frequentism found its beginnings as early as Aristotle, in a vague sense. As the world advanced to a more scientific one, we evolved to more sound, statistic measures. We wanted nothing based on just guess and check. We wanted rigorous, safe methods to calculate the probability of things occurring. It was Fisher himself who was one of the more famous frequentists, even if he was a tad crazy. Thank you, Miss Vacance. Next question. How do your methods work? Miss Vacance, we will start with you. Well, every statistical mind knows how frequentism works. I mean, it is a standard method since it's simpler and easier to teach to students who could very easily be the next great minds in the field. Inference test, μ(x)bar, inference tests based in sound samples that result in sound p-values, tests with proportion, means, even categorical data, all to predict whether or not the null hypothesis is probable or not. It's all very easy.
And easy to hack. Why do you think so many psychologists and sociologists have moved to Bayesian statistics? Yes, it's harder, but at least our values can't be hacked like yours can. Sound p-values. Bayes' theorem permits the user to calculate the chances of an event given a cause and a cause given an event, using the formula. Following. Probability of A given B. Thing you want to find out, correct? Equals the probability of B given A times the probability of A all over the probability of B. It's beautiful. And even better, it can be added to and improved as new data comes in. It isn't bound by some sample. It uses real-world data as it occurs to predict when it will occur again, or not occur.
Civil ladies, please, cousin, please elaborate on how your methods work. Bayesian stats aren't the easiest to understand.
Well, let's use the example of two horses in a race. Dogwood and Fleetfoot. So, say they've raced each other 12 times, and that Dogwood has won 5 of the 12 times, and Fleetfoot has won the remaining 7. With this alone, you would back Fleetfoot, and you wouldn't be wrong. But say on racing day, it's raining, and you learn that Dogwood has won 3 of 5 races in the rain, and only lost 1 of 5 in the rain. So, to combine these information, we need to have 4 different categories. Dogwood wins in the rain. Dogwood wins with no rain. Or dogwood loses in the rain and dogwood loses in no rain, which is 3 out of 12, 1 out of 12, 1 out of 12, and then loses with no rain, 2 out of 12, and then loses with no rain is 6 out of 12, 1/2. And you can apply this to Bayes' theorem, because it's perfect. So Bayes' theorem would say the probability, let me redo that. The dogwood wins in the rain equals the probability of rain given dogwood wins times the probability of dogwood winning, all divided by the probability of rain. And this fancy little equation, which I won't delve into right now, it will carry on, is roughly equal to 0.7501. Or, if it is raining, given that it is raining, dogwood has a 75.01% chance of winning the race.
Nothing to add to that, Miss Fickens? No. Alright then. Well, thank you ladies for attending the debate of frequentists and Bayesians. Any closing thoughts you would like to add, Miss Fickens? Statistics is an odd math. Using numbers to predict the world. It is used in almost any field of science, and different types are used as well. I will admit that the standard statistical method doesn't have a whole lot of flexibility, but is a great place to start before trying to explain the highly complex Bayes' theorem.
I agree, Mrs. Fickens. Frequentism has its uses, but so does Bayes' theorem. It is used in all sorts of AI and computer fundamentals, with an increase in so many science fields like...
And thank you, ladies, for joining us tonight. It has been a wonderful, really a fantastic debate. And thank you, viewers, for tuning in tonight to watch the great minds of the century battle it out in words. I'm Gebhardt, and this has been Statistical Minds. Good night.